Good afternoon and welcome to this session. I want to thank so many of you for joining, particularly towards the end of VMworld. I hope you've had a great VMworld. As you can hear, I've had a great VMworld, but I've lost my voice. So we'll see if I can get through this presentation and one more today. Today I have the really great honor of presenting this disclaimer. Actually, I have the really great honor of being the executive sponsor for a whole range of research and innovation programs within VMware. So we have a lot of innovation programs within the company. The goal of these is really to be looking out for, obviously, our future, but also your future as our customers. So we do a lot of this. In fact, although it's not listed here, I view VMworld as also part of that process for us because it gives our engineers, our developers, a tremendous opportunity to interact with you, our customers. And I'm sure many of you have been involved in meetings learning about sort of some of the things we're thinking about. And that ability to interact with you, run our ideas past you, learn from you about your ideas is extremely valuable to us. So from the innovation side of the shop, we really appreciate your coming to VMworld. Today I really want to focus, though, not on our, we sort of have in our innovation program some programs that affect many of our engineers across the company, and then we have certain more strategic programs that are smaller numbers of people where we're taking bets on specific opportunities. And in the past year, we've really extended that by starting the VMware Research Group. So I wanted to focus today on some of the things this activity is involved in and just how we go about thinking about things. So the key purpose of this group is to anticipate and create disruption, right? So it's, we're in an industry where things change quickly. It's very important to get ahead of the disruptions, to see them coming, and of course, sometimes be able to create some of them ourselves. We do that through a lot of collaboration with academia. So we try to hybridize our ideas with the best ideas in academia, put those together, and see what develops. And that means that we're both doing things to contribute to VMware, but we're also doing things that contribute to advancing the state of the entire field. The three people here are just three of the people that have joined the new research team. I've highlighted them here because they're sort of examples of the sort of stellar researchers we've been able to attract and the wide range of activities that we're looking at. And also because I'm going to be particularly highlighting their research. So they were sort of my co-authors, essentially, of today's presentation. So I mentioned this sort of focus on disruption. And one way to try to look for these disruptions and to think about them is in terms of pendulum swings. It turns out in our industry, and particularly in the research end of things, you'd like to think that research is very objective and scientific. But the truth is it also goes, with trends. And so, we have pendulums that swing in our business quite a bit. And one of the things to do is to notice often we'll all go down one path in a certain direction. And then about 5 or 10 years later, somebody will sort of have a new observation about how we could have made the other direction work well. And the whole field will sort of swing back in the other direction. And noticing those swings and anticipating them is very important. So we're going to talk about some of those swings today. So an example in our field is we've had the swing, if you think about it, we had batch computing was very centralized. We swung over to distributed computing with PCs and, sort of work group servers. And with the cloud, we've really swung back essentially to a very centralized mode of computing. So that's an example of one of these pendulum swings, right? We all went distributed, and then we were like, well, maybe we want to do distributed computing in terms of lots of different computers, but put them all in the same room, or put them all in the same data center. So it could feel like when we do that, we're not moving forward, right? We go over here, and then we go there, and if it's a simple pendulum, you come right back to the same spot. In fact, we are clearly moving forward hugely. So, in batch computing, we had significant limits on how much we could do on our scale. Distributed computing gave us more scale. And it's not just the number of computers it's the range of things we could compute, right? The range of applications grew. Our whole industry and the impact we have on society grew tremendously. And as we move over to the era of cloud, we grew this again, orders of magnitude of growth in terms of what we could do, being able to now touch billions of people around the world with our technology collectively as a field. But an obvious question to ask that we're looking at now is, are there reasons to think cloud actually in the next step moving back towards, say, a distributed cloud? And a good analogy here would be what's happened with the power industry. In fact, the power industry, the electrical industry, in the early 1900s, when it first started, was very distributed. You had these little generators on every stream and, sort of small rivers. And then we moved to very large power plants, and that's kind of been the model. But lately, the power industry has been moving to distributed generation. And you could imagine the cloud also moving to a more distributed model if we were able to share resources between different clouds and different premises. You could imagine, for example, if you're an on-prem customer or user and you have a big site with excess capacity, could you contribute that capacity back to the cloud the same way that, say, a solar panel installation on somebody's roof can contribute their capacity back into the grid? So these are examples of research topics that we're investigating. I'm not saying it will happen that way, but you could imagine that we may move back towards a more distributed cloud, and we want to anticipate that and perhaps even contribute to how that might play out. Now, another very large disruption that's looming for the industry, and in fact that we're already going through, is a change in Moore's law. And before talking about the disruption, I think it's just important to spend a moment or two talking about, essentially the impact or the degree to which Moore's law impacts all of us and has for decades now. It sort of fulfilled two functions, right? One is, I think of as old faithful, like a geyser, being very predictable. So the notion that every 2 years we got that doubling in transistors meant that we could all anticipate that improvement. We could design systems that maybe aren't viable today, but we know that in 4 or 6 years they're going to be viable. So we could all plan our R&D and our future based on knowing that we would have more resources, more capacity for lower prices going forward at lower costs. It was important also when I say that we could all do that. It was sort of a rising tide. So all parts of our IT ecosystem became sort of synchronized to this clock, right? We could all anticipate this. So those of us doing virtualization could anticipate it. The OS people could anticipate it. The database people could anticipate it. The folks developing apps in the enterprises, we all sort of roughly knew what the game was going to be going forward. And the problem is we've got rough water ahead. It's becoming less predictable. For those of you that follow this, you notice that Intel in their prior release over the summer, indicated, well, maybe they're now at 2.5-year cadence as opposed to 2 years. But they're, that's for the next 2 generations, and then we'll have to see. And if we look further forward, we can look, this is a prediction that one of my former colleagues, both at Intel and at DARPA, Bob Colwell, made. And he sort of said, gee, not only is it getting less predictable generation by generation now, but if we look into the future, it looks like the one trick that we've been playing, which is constantly shrinking the size of the transistors, which is not the only way we can get improvements, but that one trick is really running out of room. And the reason Bob says this is basically because the silicon lattice, which is, we make these transistors today on CMOS with silicon, and the spacing of those atoms is basically 5 angstroms or half a nanometer. And, if you think about it, as we get down as an industry to 7 nanometers, and then you start looking beyond that, you just you're running out of atoms. Okay, so we either have to change how we make transistors, which is one possibility, or we, essentially run out of space. So there's definitely going to be some significant changes here. And I'd argue that this has actually already been going on. Remember, I talked about how this has been a rising tide. We all moved together. We've all been synchronized. But in fact, if you look, the cost of staying on that technology curve has already caused a number of companies in the industry to say, you know, strategically, we're going to decouple, we're going to get our innovation, we're going to get our improvement in other ways. And so this process of the less predictability and the less kind of synchronization and coordination of our industry has actually been underway for some time now. And, you know, part of my message and our research team's message is, you know, it's okay. There will be innovation beyond this, right? The world's not coming to an end. There's still many tricks we can play. First off, on the technology side, the semiconductor side, we'll see people bring new materials, and we'll see changes that way. And we'll also see new architectures for how we design processors. So we'll continue to get innovation from the hardware, but it won't be as predictable. And that means we need other ways of kind of coordinating and working as an industry together in order to ship things that work for everybody. Now, getting back to sort of that pendulum swing analogy, if we look at it and think about this, what's really been going on for the past 40 years is we used to have a very heterogeneous technology base. So for example, we used to make transistors out of a lot of different things, not just, you know, essentially silicon. And we used to wire them together in many different ways, not just the way we put CMOS together. We had TTL, we had ECL. Some of those things still exist, but they're really, you know, off in the fringes. And so we got in a huge efficiency by becoming more homogeneous, right? So one of the reasons you've sort of gotten all those cost decreases hasn't just been more, you know, the kind of Moore's law shrinking of the transistors, but we kind of put all of our muscle behind one way of doing things, that homogeneity. And we've done the same thing with the processor architectures, right? The convergence on x86, particularly for servers, we drove out the other architectures, we converged on one thing, we got huge efficiency as an industry, but as we did that, we moved further and further out on that cliff, right? And we now have to come back out from that edge. So what we think as a research team is happening here is the pendulum is now going to swing on the platform, the hardware side, from homogeneity back to heterogeneity, and that it's actually already underway. That process has been going on. So if we think about this, one of the things you've seen is we sort of used to have frequency scaling. That stopped. So the single thread performance, you know, we now have a little, frequency goes up a little, but not very much generation to generation. Then we had the increase in core count, and that's been very beneficial, but that is also sort of likely to come to an end simply because even when we get more transistors for energy density reasons, we can't necessarily use them all at the same time. So that encourages us towards having specialized features on the processor chips, right? So you're starting to see, this is something that's been going on in mobile for a long time. If you look at a mobile device today and you open it up, you'd find the ARM processor in it, but you'd actually also find a camera processor for still images, a video processor, an audio processor. You'd find, and these are all very high capacity parallel processors. They run at lower frequencies, very efficient energy-wise, but are very parallel. So in fact, the client end of computing has already been going through this transition for quite some time. What we're now seeing is the server end starting to go through this transition. So you're seeing sort of integrated GPUs, integrated crypto within servers, and people now looking at also adding FPGAs. So if we think about how that affects us in terms of virtualization, and virtualization is not the only thing we study at VMware, but it's obviously pretty important to our business and our interests. One of the things that we've been able to do when we virtualize CPUs is we've kind of taken advantage of that homogeneity. So we could sort of have a fairly homogeneous view of what a CPU is and give you a homogeneous model of that, and a fairly, you know, clean model of what a disk is, a virtual disk. And maybe there's a couple flavors, but it's, you know, fairly small number and a fairly good idea of what a VNIC is. Going forward, if we look just at the processor, looking at the right-hand side, what you're going to see is you're going to still have x86 processing, but now we've got this GPU capacity and we have this crypto capacity, and a little bit further into the future, we see this FPGA capacity coming, and we have to learn how to virtualize all of that. and to be honest, to provide much better programming models for all that. Because it introduces a number of not just virtualization, but if we sort of push above the virtualization level to the programmer level, a number of interesting challenges. You know, one is not only are many of these almost all these new types of processing elements are highly parallel themselves, so you have concurrency when you do GPU computing, you have concurrency there, or your FPGA is inherently concurrent, but those things are running concurrently with your x86 processor that's on the same chip. So you've got to synchronize that. You've got to think about how you move data between those different processing elements, and generally how you deal with the different programming models in those elements. And today, that's basically all left to the programmer. So one of the areas that we're certainly conducting research in is to think about how do we sort of provide a much more coherent model, not just the virtualization, but overall programming model to folks going forward. So that's just one way that we can deal with, as I said, the traditional Moore's law coming to an end as we start dealing with the add back of more heterogeneity into the underlying processors. So that's one thing that we can do, and we're conducting research to work on that. There's another thing we can do, which is kind of a convenient timing situation. When I think about research and I think about what are opportunities, one of the things I sometimes do is say, where are there places that the academics have piled up a lot of intellectual water behind a dam? You know, this happened when I was at DARPA a number of years ago. I could see this with statistically based machine learning, so we made some very big bets there, and those paid off. We could see that there was a lot of capability there that the academics had sort of piled up, but it hadn't been translated into applications. And I think we're in a similar situation with algorithms, that there's been a lot of progress in algorithms. Now let me explain why I think that's important. If you think about what we've been doing for the past 25 years, we've been in this situation where the hardware guys kept delivering up to us more and more capacity at lower and lower costs. And because we could count on that, we could essentially think in terms of what I think of as creative waste. We got really good as an industry as just using cycles, right? We'd always be asking, what are we going to do with those more cycles when we have them? How are we going to take advantage of them? And personally, when I was a junior faculty member, this is kind of how I made my career. I worked on desktop video. At the time, everybody thought that was crazy. Video was done on hardware. But we looked and said, well, we're going to have plenty of cycles, so we could use those cycles. We could do all that compression in software. Stop doing chips for hardware compression. I worked on what's now called software-defined networks. Same sort of story. Software-defined radio. People thought that was sort of a crazy notion. But these were all examples of essentially creative waste, right? We looked and said, we're going to have lots of capacity. What could we do with it? That was a big pendulum swing from a prior era, certainly when I started in the field, where we really worried about optimizing, every little byte, right? If you were working on mini computers and you had small amounts of memory, small amounts of computation. So we moved from that area of efficiency to creative waste. We now need to move, I think we're going to have a big swing back to worrying about efficiency, and it's going to count in a much bigger way than it has in the past. And at the same time, I really want us to maintain the budget for creativity. I love the fact that we've been able to expand the range of applications, do more and more things with information technology, touch more people's lives in more interesting ways. So we have to think about how could we use these new algorithms to essentially claw back inefficiency, right? So we basically use the algorithms to sort of buy ourselves back a budget of kind of a currency. We get back the inefficiency through these new algorithms, and now we could apply that to whole new areas of creativity and develop the next generations of opportunities and new applications to grow the industry. So I just want to give you some examples, and if you're thinking, well, is there really that much? Can you really get that much back in terms of inefficiency? Now, this is an extremely contrived example, but it's a great example from my colleague Charles Leiserson at MIT. And it's an example of optimizing 4K by 4K matrix multiplications. Now, how many of you do 4K by 4K matrix multiplications every day? Right, okay, so it is a little bit of a contrived example. Now, actually, to be honest, you're doing more than you think because it's actually, these things are actually embedded in a lot of the things that you use. So you're probably doing more than you think, but I'm admitting that this is not the thing that most of us spend all of our time on. But the example is still illustrative. He looked at, what happens when you code that in Python, and what's the gap between that and the best code, kind of most optimized code we know. And the important number here is the number in the bottom right corner. There's a 55,000-fold room for improvement, right? That's a lot of Moore's Law doublings, right? We can keep, we can keep the party going for a long time. Now, I'm not saying we can get 55,000-fold improvements in everything we do. I'm just trying to show you that there's a lot of room on the table in a lot of innermost loops in a lot of places. And what's really neat here now is we've hit a point recently where computers are actually exceeding humans at being able to do this kind of optimization. So it's actually, this is kind of a funny thing, which is because we have a lot of cycles, we can use that creative waste, but throw the creative waste at optimizing the stuff that we run every day. And what I mean by that is, so imagine, one of the tricks you can do now is it used to be the best way to optimize code was human hand optimization. But imagine you have an innermost loop and you have an instruction set like x86 and you said, you know what, I'm going to try all the possible sets of instructions to achieve that loop. Okay, you're going to do at least as well as any human. Now, we don't quite do that. There's some games you can play to exclude a whole bunch of cases that you don't need to try. So you don't have to necessarily try every possibility. But the bottom line is you can throw a lot of cycles at that innermost loop once, and then you get the benefit of that forever, right? And so it's a really kind of interesting example of using all this horsepower that we have, but using it now to make everything else more efficient and to claw back inefficiency once and for all. And I think there's a lot of these kinds of opportunities. That one was just a code optimization. Here's a more generic statement of the situation. And by the way, we have a researcher that specializes in that kind of optimization that I just mentioned. We also have somebody who's one of the world experts on dynamic algorithms. This is kind of interesting in the sense that something that's bothered me for years and years is I've often felt, our code is full of function calls. Don't you feel like often we actually pass the same parameters into those function calls over and over again? And we just keep evaluating the same function with the same inputs and getting the same outputs. So it sort of feels like, hamster in a cage. We keep just doing the same thing over and over again. And that's all wasted cycles. So the more generic statement of that is that most of our algorithms that we use today for things like graphs and data analysis and scheduling do that sort of static analysis. In other words, every so often you rerun, you make a change to the graph, which could be, say, when you're doing a map, you've got a map and you're trying to find out how to get from A to B. Every time you make a change to the graph or you move a little bit, we redo the whole thing, the whole computation. So that's great when you think the cycles are going to be available forever, but it's also sort of silly. So dynamic algorithms would basically say, okay, we could, when we compute the graph the first time, bury a little extra information in the graph, right? We're going to pay a little overhead so that when you make a change in the graph, we don't have to go and do the whole computation all over again, or at least we don't have to do that every time. Maybe if the change is a big change, you'll decide it's more efficient to do that. So we can see a whole shift from one type of algorithm to another. And I have to tell you at this point, it's really strange for me to be standing here being, this big champion of algorithms. I'm a systems guy, networks and operating systems is what I do. But I'm starting to see that we have this huge opportunity to take advantage of the stuff that these folks have piled up and really take advantage of it. So another major transition is moving, and this is one that's been underway for a while, from a world where we focus on precise results to taking advantage of approximations and realizing that in many cases an approximation will suffice. And there are many systems that do this. Obviously, when you use web search, you're not going to look at all the possible answers that come back. You'll look at the first few pages of answers and you'll probably be satisfied with what you get. So you're essentially accepting an approximation there. And we do this a lot in our daily lives. So some underlying trends there that drive you towards working with approximations. One is, if you've got a big data environment, you've got all this data, but by definition, a lot of data is going to be spread out across a number of storage devices, so you can read some of it more efficiently than others, right? Some of it's going to be closer, some's going to be further away. And if it's a really big distributed system, by the time you read things, things may have changed. And that's very true. I'm a networking researcher. In the network environment, when one of our big issues with congestion control and analysis is by the time you get the information on what's congested in the network, it's already out of date. So we always are thinking in terms of round trip times and the time constants of algorithms to adjust. So you actually, in certain cases, have to settle for an approximation because there's no way to know what's going on at the particular moment in time. So the tools that we use for this are primarily statistical tools. And if we want to make statistical judgments, we have to assume that there's some element of randomness because those again, are the tools that we have available to us. And we use that to create approximations and try to get error bounds. This is the important thing, is do we understand the error bounds in those approximations? So this is an area that I think is really, again, very ripe because the tools here have gotten dramatically better. We can use this a lot more going forward. And I just want to give you one example that sort of now brings this back to, like, why does a systems person think in terms of this stuff? So an example of, one of our researchers who's an expert in this approximation stuff, looking at load balancing. And, the basic load balancing problem is essentially the basic hash table problems. This is something that we all learn pretty much in our first computing course, maybe the second course. Is to use hash tables. And if you think about it, we don't always think this way, but hash tables are one of these randomness things, right? You hash the thing into a random bucket, or you hopefully that your algorithm produces a good distribution. It's not necessarily fully random, but a good distribution. So the idea is to put these things into buckets as they arrive and try to balance things across the system. Now, the reason that we don't, in an ideal world, we would not have any one bucket. We're trying to do either, load balancing. We don't want any one processor to be overloaded, any one file server to be overloaded. But if we wanted to do this perfectly, we would have to keep track of the state of all the buckets, right? And we'd have to remember where everything was placed and everything else. And so, we settle for something that's not perfect, but we'd like to keep it from being too imperfect. So if we just use simple hashing, which, as I said, we've all learned, we end up spreading things, and occasionally, like you'll notice, bucket 5 here is a little overloaded, and buckets 2, 4, and 7 are sitting empty. So we got, it's not terrible, but it's imperfect. As our systems have gotten bigger and bigger, we start worrying more and more about the outlier cases. So probably many of you, we used to worry about what's the average performance of a system. Now we tend to worry about what's my 95, what's my 99th percentile, right? We want to worry about those tail distributions. So now the notion that every once in a while you might get a real outlier, bad distribution in your hashing, that's a big problem for us. So could we do something to reduce it? And there's been this sort of cool observation in the algorithms world for a few years ago about something called the power of multiple choice. And to me, this is like building a better mousetrap. I mean, I'm surprised something that has been around for so long, like hash tables, that you can actually see a substantial improvement on it. And so basically what you could do is say, instead of choosing one bucket, I have a hash algorithm that tells me one place I could put it. Let me have a hash algorithm that gives me two candidates, two victims. And then I'll go look in those two places and stick the ball in the one that's least loaded. And that simple change of, instead of always putting it in one place, being able to choose between two, dramatically reduces the tail latency, or the tail distribution. So it's still you could have an outlier case where things are bad, but your chance of being in that outlier case goes down considerably. So it doesn't really change your average behavior, but really helps you tremendously with the tail. So it's pretty cool, and it's not a lot of extra effort to do it twice. Okay, so we do a little bit more work, we get a much nicer distribution. So it's just an example of sort of progress that's being made in these areas. Lots of research questions still remaining here to be resolved, and that's, of course, what Udi is hard at work at. Now, again, the theme here is some of these pendulum swings that we're seeing in the industry. This is another one which has to do with consistency. So in the earliest days of our field, when it comes to transactions, we did things we called transactions, but we didn't have a formal model of what they were. We didn't know about ACID properties or any of that. So to be honest, we built systems that made mistakes, right? And they just had, various bugs in them. And then Jim Gray and a few others figured out a sort of very precise statement of what properties we needed to preserve, the ACID properties, to get reliable and consistent transactions. And that's what we think of as sort of strong consistency guarantees in the field. And that allowed us to scale up. Like those early error-prone transactions, if you weren't doing a lot of this, it was okay, it didn't happen too often, right? With ACID, we could scale up to do things like online banking in the 80s and in the early 90s. And that was good. That allowed us to get more scale. But then the web came along, and we now wanted to do things at much bigger scale, and we didn't know how to scale up ACID. We could do it distributed, but it still sort of had a lot of places where it slowed us down. So we kind of fell back to weak consistency. It was a little better than the earliest days where we didn't know what we were doing. Now we sort of had a description. We understood that things could go wrong, but we sort of had a feeling like we knew when and where and how they could go wrong. Well, that worked out well for quite a while, and it worked out well when the people, if you had only a small number of people building these kinds of systems, and those people were, some of the world's best folks, and they understood exactly what their weak consistency semantics were, what worked and what didn't, and what the corner cases and all that were. The problem is you can't have 1,000 people or 10,000 people building weak consistency systems, all of whom are the 10 best in the world. Okay, it just doesn't work. So we need to think about how could we continue to scale this up, and could we get back to the good stuff? Could we get back to strong consistency? Because the weak consistency was starting to fail us. And an example here is, at Amazon, they built Dynamo with a weak consistency system. And you notice it was followed by DynamoDB. One of my rules for researchers is you can change the name or you can change the technology, never change both at once, right? So DynamoDB was totally different from Dynamo, but they kept the name. And so the key place that we see a movement today is back towards transaction systems that have strong consistency, partly because some applications need it, because good enough most of the time means that you're not good enough of the time that it really matters to your customers, right? And the second reason that you need it is because, to be honest, the world doesn't have enough people that even knew how to make sure it was good enough most of the time, right? So some of our researchers, and this is work that they started doing before they joined us, and they've been continuing since they joined, we're looking at this and trying to understand, what allows the weak consistency systems to scale, and could we kind of get that without giving up on the strong consistency. And the big thing that allows the weak consistency systems to scale is that we shard them, right? So we do scale out of transaction systems, and that's cool. We all love scale out. Now, each of those ends up needing a lot. Actually, I'm going to back up a step here. The catch is that after we shard them, we need a way to put Humpty Dumpty back together. So we shard them out, but then we need to add a name service, a lock manager, transaction management, the caching, and it's all those boxes at the bottom where the hairy, weak consistency stuff falls in. The observation that our team had was that each of these pieces ends up having a log, and it's inconsistencies across the logs in the different pieces that mess you up. And they realized if we could come up with a way of having a high throughput shared log that all those pieces could share, then you could have the benefit of sharding and the benefit of scale out, but still have the consistency. In other words, all you needed was to figure out how to have the log be essentially shared and consistent. So then they looked and said, what's the minimum part of the log that's screwing us up? Is there one piece there that you really needed to sort of figure out how to do? And could you, this is classical computer science, right? Move the problem around, use essentially pointers, use a level of indirection. And what they reduced this down to is if you could have, they used the word soft state sequencer, that's fancy jargon for saying a counter. So if I could have a centralized counter, I could reduce this problem to saying I have a centralized counter and everything else can be widely distributed and scale out. And you know what? We can count really fast. So from a throughput point of view, having a centralized counter is really not a big problem. Right? So with that centralized counter, you can now build this shared log that's distributed. You can now build all these systems that are distributed and get strong consistency back. So this is pretty cool, and this is embedded in a system called Corfu that we're working on, and it's actually being open sourced. So this log becomes the source of persistence, the source of ordering, your version history. It provides a snapshot capability and checkpoint capability. And of course, you have to have some capacity to trim the log. And with that, you can then, on top of that shared log, build particularly a whole range of in-memory data structures and systems, whether it's key value stores, databases. In our case, for our network team, it would be SDN controllers or your favorite application. So this is kind of I think a pretty cool example of the pendulum swinging back towards strong consistency and researchers figuring out how to do it at massive scale. So we've kind of moved the bar forward. We now get the massive scale and the consistency, the good stuff. So as I said, this is an open source project, Corfu, and you're welcome to join and participate. So it's hard to give a talk in this sort of audience these days, and I want to check my time. Yeah, I'm doing okay. To talk, you got to talk about Internet of Things a bit. I wanted to know if I could talk a bit or talk a lot. And I think you probably know most of these things, right? It's about connected devices. I emphasize the connected because we've actually had these devices out in the physical world. When I was at DARPA, we did what I think is the first inventory of what was the rate at which embedded microcontrollers were being put out into the world. And it was about 6 to 8 billion a year, and that was in the late 90s. Okay, so now it's in the tens of billions of devices a year that we've been sort of foisting out there on the world. So we've actually had these things getting smart for a very long time. The thing that's changing is we're finally getting them networked, and that's not by accident, right? That's been a deliberate research agenda of many people to facilitate the networking of these things. So it's getting these things connected that's the new thing that's different. They link the physical and virtual world. By doing that, we enable productivity gains and that contribute both socially and economically in many interesting ways. And then I'm going to add the key bullet that you may or may not have thought about. It's absolutely critical that this be done and they operate without human intervention. And I'm going to come back to that bullet later because I think that's one that's often missed, and that's in fact I think the big disruption that's looming with IoT. So as I indicated, I've sort of been involved in this for many years, and I'm also on the FCC's Technical Advisory Committee. So a couple of us co-chaired a study for them last year. And one of the things that was interesting to me was to see, okay, I haven't been as involved in IoT lately. What's really changed in IoT compared to the vision some of us had 15 years ago? Now that it's really happening, how is it rolling out differently than we might have anticipated? So some of the key changes, one cool one is we now really have this ubiquitous network. The cell phone network has rolled out in ways that we really, it's kind of been beyond our wildest hopes in terms of the capacity and the global footprint, particularly with LTE, now that you can have, megabits and soon gigabits to pretty much anywhere in the world. Another big change, though, is the notion of cloud computing, and that these things will, pretty much instead of being, transmitting their information to, say, a local on-prem computation capability, they'll be likely transmitting their information first to the cloud, and then it will go to wherever it's being used. So the thing, and I'll sort of give you examples of that. If you were trying to produce, and this is from my VC days, if you have we had a company that was producing a diagnostic reader. It reads, I've got a sore throat here. Actually, my throat's not sore, I just have a hoarse voice. If I had a sore throat, I'd want to get a strep test. And this device reads strep tests. Now, the obvious thing is you're right in the doctor's office. The thing should just provide the results of the strep test directly to the doctor, you would think. But to do that, it has to integrate locally with all the information, all the, with the local Wi-Fi, the local lab information system, all the local stuff within the doctor's office, and that stuff is constantly changing, and that integration is very fragile. So one of the things that we learned that was sort of surprising is it actually makes more sense for that reader to send its information up to the cloud, to a cloud that's operated by the folks that provide the diagnostic reader and provide the actual diagnostic test, and then integrate with the doctor's office over the top, XML to XML, cloud to cloud. Because actually we know how to do cloud to cloud integration really well, and it's not very fragile, whereas the local integration stuff is. So that's sort of significant change, that many of the people that sell these things are actually going to sell them, with a service. So one of the other changes is the business models in terms of pay per outcome and consumerization. But often the thing will essentially be drop shipped to a customer, and it will directly upload to its own cloud, and the way the customer will get the information is on a cloud-to-cloud basis. So that's a significant change in how we imagine things happening. Another big change is the security and privacy environment, obviously. Somewhat affected by Snowden, but also by things like the Sony experience, the Dropcom experience, most recently some of the automotive industry experiences. And as we looked at this, what we realized is that it's going to be very hard to secure the things that are at the very, very edge, the very dumbest, cheapest things. You're going to be able to secure them on day zero, but to keep them secure over their lifetime is actually going to be very hard, because they probably aren't going to be fully software upgradable. I'm talking about now the things that cost a fraction of a cent, right? And the crypto on them may not stay secure for that 8 or 10 year lifetime that they will actually have. Even if you're planning on a 4 or 5 year replacement cycle, a lot of them will still be there in 8 to 10 years. So you start looking and saying, well, what can I secure? Well, those things will end up talking to a local aggregation point. Sometimes they're called gateways, sometimes concentrators, sometimes an aggregation point. And the architect in me hates these things, these gateways, because I'm an end-to-end guy, and I'd really rather think about an end-to-end model between the thing and the cloud and ultimately the user of the information. But I think the reality is that these gateways or proxies are going to be a critical place that we can actually secure and manage, because we can expect to upgrade those gateways more often. We can expect to manage their software. We can expect to maintain a strong security, at least to the gateway, and maybe the last couple meters we have to accept is a little less secure, but then of course you have geo-security. Somebody has to get within a few meters of the thing to have an impact on it. And I'm not saying that's a perfect security story, I'm just saying as we thought about the reality over the lifetime of these things. So the role of gateways and aggregation points, and I've highlighted both the biggest changes I see from the past 10 years, the cloud and the role of these gateways. So as we think about it at VMware then, we have data capture and analysis. We always knew that anybody in IoT is going to have to worry about get the data and crunch on the data. And the two things that get added are the thing management now becomes really important over the lifetime of the thing, and particularly the management of those gateways that are the sort of first aggregation point that you can count on that talks to the thing, and cloud mobile security service delivery. Those are sort of the things that we add to the picture that weren't there 10 years ago. So drilling down just a little in thing management, One of the places we really expect to participate ourselves as VMware is in, securing and managing the gateways in particular, and securing and managing the things. This is an area that we think we can uniquely help you with. We already do it at AirWatch, so we see this as an interesting way to extend our learning, take advantage of what we know about being able to do this, over-the-air update, all those things. Same way we secure and manage your mobile data on your BYOD devices, to be able to secure and manage the gateways. So this is part of where I see sort of us playing in the world as it's evolved and as it's changing. This is, I've already kind of covered that, secure and manage. This is an example of one project that we have going with Coke, where they've introduced these new types of beverage dispensers. You'll start seeing them. There's thousands of these out there already. Tens of thousands actually, but you'll start seeing these in restaurants and other places where you can basically, mix your own drink, right? So you can get your own beverage mixed exactly the way you like it. So it's kind of an interesting innovation, and we help them secure and manage that dispenser. Effectively, we're securing and managing the main controller in that dispenser. It's going to have a whole bunch of microcontrollers deeper inside it as well. So that's, kind of one example of where we play. If you think about us in the broader federation, and, you see that there's, in addition to what we can do with AirWatch, we're also using vRealize operations to manage gateways. It's another interesting development. I just didn't have time to drill into it. Log Insight to be able to manage the logs. So a lot of the tools and the things that we've been doing can be extended. And this chart just gives you, sort of other places that both we VMware play or other parts of the federation. One that I just would like to highlight is, I think it's pretty exciting to me, is NSX, and the opportunity to extend NSX to those gateways so that you get a secure networking environment and a micro-segmented networking environment all the way out to the Internet of Things. So, we're at the stage with this. Again, it's still a very early incubation activity for us. So really the thing that we're doing is proof of concepts. I think the most important thing with these things is, before you go out and do that whole architecture and implement it all, go work with customers and do trials with customers. So that's the thing that we're most working on. And that global beverage company, this chart didn't get updated, but it's obviously Coke. We just only recently got their okay to use their name. So in wrapping up this IoT thing and wrapping up the whole talk, I want to come back to that comment I made about how what I think is really important about IoT is that these things need to run unattended. And that's a really big change for us, right? Our computers, our laptops, our mobile devices, human beings are at the other end of them. That has advantages, and of course has disadvantages. Those, and from the IT point of view, having users go and change stuff is not always a good thing. But knowing that there's a user there that can go and change stuff, or that can notice when something's gone wrong and can intervene, is essentially our ultimate fallback to date. And we can't have this going forward. Now, I want to kind of put this in a broader context of how we got here. In the early days of computing, everything was batch. It was batch computing, and you would write up your program, you'd get your data, you'd put your data in, and eventually you'd get the answers back. And then a group of researchers in the 60s had this vision of interactive computing, which was also called human-centered computing. And they were basically saying, well, what if people could interact with a computer? For one thing, what I'd like to do is give the computer some data, get some answers, give it more data, right? And go up and back like that with my computer. And in fact, I'd like to talk to my computer, and I'd like my computer to have machine vision. And all of this stuff was actually envisioned, and the kind of research agenda started in the mid to late 60s. And we've been on that path for a very long time. It's now actually getting to the point where we can do some of those things that we wanted to do. And the catch that we saw in the late 90s at DARPA, and this was seen by other research managers elsewhere in the world as well, is we'd all been working towards this vision of one computer per person and people interacting with computers. But even in the late 90s, the lead users were already using multiple computers, and they were starting to have mobile devices. And so we were getting to having tens of computers per person. And as I said, we took that inventory of all these embedded devices and realized we were headed to a world of thousands of devices per person. So here's the question. Do you want to interact with thousands of devices? Right? That would be, horrendous. When I was, at DARPA, the way I'd put it to the generals, it's we are putting human beings in the direct line of fire of information technology. Right? It just doesn't make sense to do that. So we need to move to a model where we interact with a few computers. We keep making interactive computing better, but the vast bulk of these embedded computers, and particularly these things in the IoT world, are proactive. We don't interact with them. They anticipate what we're going to need. They sometimes take actions on our behalf. So we need to sort of make that flip. And the research community has actually been investing in that for quite a long time now. And we're just at the cusp of being able to, I think, get that best of both worlds. So that's the last kind of meta disruption I want to leave you with. Because, in our field, we have the changes that happen every couple years. We have the changes that happen, say, every 10 to 20 years, like the move, from mainframes to minis, and then minis to PCs, and PCs to mobiles. And then you have these big changes that are like 30, 40 years. And I think that's one of the big ones that we're going to go through right now. We've moved from batch to interactive. That's how we've all enjoyed our careers. And now we're going to move from interactive to proactive computing. I think that's going to be a very exciting space for us going forward. So with that, I want to remind you to please fill out your surveys and take a few questions. I think there's people with microphones if you have any questions. Any questions? Yes, gentleman over here.
You speak of randomization as a possible solution, but isn't that just one of the biggest problems in IT, to get real randomization to work to our advantage?
I'm sorry, I missed the very last part of what you said.
Well, is that not one of the biggest challenges? Because randomization in IT, well, it's a contradiction in terms for most parts. At a certain point, it will be repetitive.
I guess the point I'm trying to make with this is that if we want to trust approximations, we have to think in terms of a distribution. So we have to have some mechanisms sometimes to deliberately randomize the traffic. Let me give you an example in networking, which is if I want to have a load balancer, I need to have some way of spreading things across, and I want to introduce some randomness that will sort of smooth out the balance of that traffic as I shift things through different places. We do this, it's actually in switches and in other places. Does that make sense? So I think where you're headed is saying, I don't want things to get too random, and I don't want to get unpredictability. But you can think of randomization as also giving you an ability to then apply statistics and have a better understanding of what the possible outcomes are and what your outliers are. And then you basically design for the case to say, statistically, my chance of failing is, for example, lower than the chance of a hardware failure anyway. All right, and then you sort of feel like, okay, so I'll treat it like a hardware failure. It doesn't mean we want to introduce systems that behave randomly to the users.
Yeah, hi. So since we're thinking the big thoughts and far into the future, would you care to comment on AI?
On AI in general. So, the comment I made on AI many years ago is, and it applies to a couple places in our field, we always use AI to refer to all the parts of AI that we haven't figured out yet. Right? As soon as we learn how to do something, we take it out of the set. There's a couple other places we do this. Like, within AI, robotics is an example where as soon as we figure out to do something in robotics, the researchers call it industrial automation, right? Or we'll call it self-driving cars, autonomous vehicles. so that they're always left with robotics as the research agenda. So I guess what I'd say with AI is one of my frustrations with that community has been that they haven't been able to sort of break it down and say, here's the 5 things I need to do. And when I get these done, we'll be there. So it's always the unfinished part. That's kind of my highest level comment. I guess my other comment is, if you're asking about how close are we to, computers really being able to mimic human beings, accurately and fully, I think we're still many, many years away. The notion of us being very close to an inflection point, I don't see that at least, 30, 40 years, possibly longer. I will say, though, in the meantime, boy, the AI, we've gotten some great things, right? So all this machine learning, all the pattern recognition, all the correlation, so all the machine vision, it's been a great ride. So it's been a wonderful investment. The consciousness part is what I thought you were referring to. Yeah, we're very far from that. I don't think we're even scraping the surface. Sir?
Yes, I was wondering if you would comment on Bitcoin, for example. You mentioned centralized, decentralized. It's some sort of the same evolution going on, and what are your thoughts on that?
Yeah, Bitcoin's, it is an area that, maybe next year we'll talk about, because we are starting to look at in our research team. I didn't want to start talking about things that we weren't already doing, as opposed to things that we're just getting started on. But since you asked, so if you dissect Bitcoin, one of the interesting parts is it provides essentially, we talked about logs, right? It effectively provides this shared log, but now in a very distributed across a wide community. And in a way that doesn't require the same levels of mutual trust. So you can essentially federate partners that don't trust each other. So it kind of provides a Byzantine challenge type environment. So that's the part we think is most interesting, right? In other words, the currency part, when you start looking at this, Bitcoin as a currency, I'm now going to give a personal, not a VMware opinion. I'm very skeptical simply because, ultimately governments are bigger than you. And, companies sometimes think they're bigger than governments, but, at the end of the day, ultimately governments have, the way, an executive in another company put it was, they've got the tanks and the guns, right? So I also think that even separate from the government issue related to currencies, the reality is you want to know what is standing behind the currency, right? Currencies, I love virtual stuff. I love everything virtual, but currency is the ultimate virtual stuff. And the only thing that makes it valuable is that somebody's standing behind it, or some entity, in this case, governments. And so if you don't have entities standing behind it, I don't see it working. So I don't see the currency part as interesting. But that distributed log, that is really neat. There were efforts to do something similar about 20 years ago where people would actually publish essentially a digest in the newspaper every day. It was a digest of all the transactions that have been done. And it just never got traction. Many ideas in technology are ahead of their time. And that's what I've learned over and over. The issue is, when's the right timing? So what Bitcoin said to us is, now's the right time to have shared digests of these sorts of transactions. So we are very interested in what we could do and what we could do with you, our customers, collectively to create that sort of shared digest capability. So and it's proven that it can be done, right? So we have the existence proof now. So I think that's very cool. I think we're pretty much out of time, or one more question? Well, she isn't saying no, so any other questions? All right, well, thank you for staying so late through VMworld. I really appreciate it.